Welcome to lesson 2 of difference equations. This is the first of 2 lessons where we handle first order linear equations. We'll talk about a general formula, geometric growth, and then compound interest as a particular application. Where we left off from the lesson 1, if you recall, we had 4 different classifications: order, how many terms you needed to look back to figure out the next term; linear, the sequence terms, in other words, the x's appear to the first power. So you can see in this equation here, it is first order and it's linear. Homogeneous, no standalone forcing term. Well, unless b sub n is 0, then this would be non-homogeneous. Autonomous, every coefficient is constant, so that would require this a of n to be a constant in order to be autonomous. So this is a general order 1 linear equation. It may or may not be homogeneous or autonomous based on what we just discussed. And we're going to solve this in general in this lesson. I carried over our general equation from the last slide. And what I'm going to show here is the algorithmic solution. So you're given x0 and then you plug that in here to get x1. So you get x1 equals a of 0 times x0 plus b of 0. And this is x1, so you plug that back in here, and then you're going to have a1 times all of this. That gives you the first 2 terms here, and then you add in b1. Then you take all of this, you plug that in, times x2, and you add b of 2, and that's what you get here, and that'll give you x3, and then of course it gets longer and longer. So this works on a computer. It might work with pencil and paper too, because recall the what you're plugging in here at the next step, this is just one number. So it looks like it's getting longer and longer, but you're just computing one of these and then plugging it back into the equation. I copied the last term that we computed on the last slide. And we want to look for a pattern here. You notice x0 appears each time. So even x5, we would have an x0 here. It's just multiplied by all the coefficients up to 1 less than the number here. And then we also have a pattern here. You notice that this, when you have 4, this is 1 less. Then the term before that has a3. The term before that has a2 and a3 times it. And then the term before that has a2, a3, excuse me, a2, a1 times it. So then that pattern continues. So we can make use of this to write down a general formula. So I took the equation, or the pattern I should say, that we recognized on the last slide, and I wrote it in terms of a notation here. You notice this is just the product of the coefficients up to n minus 1, where x is n here. So that would be this here. And then this product in here is just modeling this here, and so forth, times the bj, and that just goes until n minus 2. You notice this is a 2 less than that. And then you have the bn minus 1, which would be this here. So this is the general format. It's kind of ugly looking, but it holds for any x sub n. It's a monster. Yeah, it's kind of ugly looking. So why do we derive it? We would rarely evaluate this directly. Its value is that every case worth having falls out of it in a line or two. The rest of this lesson and part of and lesson 3 is spent collecting those cases. So what I'm saying here is that normally you'll see a pattern and you won't have this ugly equation. You can just write it down as a simpler equation, but we'll see that. It'll become obvious when we do some examples. So I have a simple example here. We'll let our an equal a, so that's a constant, and b of n equals 0. So now we do have homogeneous and autonomous. The equation becomes this now. And so when you put in, well, we'll put in x0 and you get x1, and that's a times x0, and then you plug that in to get x2, and then you get a squared, and so on. So the formula falls out pretty easily. It's the geometric series, and I'm showing that here. And that alone gives you a lot, and we'll see an example where we do compound interest, and that falls into this case here. All right, let's continue. I have more examples. I took our example from the previous slide. I let x sub 0 equal 1, and then we just have x sub n equals a to the n. I have a few examples. If a is 1.3, you keep getting bigger and bigger numbers, so it goes off to infinity. If a is less than 1, for example, 0.7, it just keeps getting smaller and smaller and converges to 0. It's the white line. If a is negative, but absolute value less than 1, then it'll get smaller and smaller, but it'll alternate between positive and negative, like this here, and eventually converge to 0. Then the other case would be if a is less than minus 1, less than minus 1, then it would oscillate, but it would keep getting wider and wider. So you would start it, they all start here, but then you would go down and up, and I didn't draw it here, but it would just keep getting wider and wider. So it would go off to plus and minus infinity as n gets larger. Compound interest is a classic example of a geometric distribution. This is how it works. You have an initial investment of p units, dollars, whatever your units are, and then there's a nominal rate of r, and it's compounded k times a year. So you divide the year up into k units, for example, 12 months, and then you divide your rate by k to get how much interest is accrued per period. That's what this is here. So you start with p, and then after the first period, x1 would just be x0 would be p plus r divided by k times the p, the principal. So it's principal plus the interest you made in the first period, and so on. So that continues. So this is in general. If you're at period n, you want to know how much you have at period n plus 1. You have whatever you've accumulated up to the previous period, n, and then you add the interest over that next interval, which is r divided by k, and you get this amount. I just factored out x to the n here. So the constant multiple is a, and that gives our formula. Just the word about the this term here, nominal yearly rate. So what that means is you can divide your rate by k. So if I said it was 10%, let's say 12%, to make it easy. Let's say it's 12% nominal yearly rate. Then the monthly rate would just be 1%. However, if you compound every month and you use that nominal rate, it's going to end up being more than 12%. So just be cautious there what this means. Okay, so let's continue with the example on the next slide. So we're just expanding the geometric series here. Remember our a was 1 plus r over k. So you get x1 is this, and x2 is p times this squared, and so on. So n counts the compounding periods, not the years. So for t years, n equals k times t. So if you invested money in an annuity, for example, and it was 30 years and compounded monthly, your N here would be 12 times 30, so it would be 360. So just be careful of that. A bigger K, in other words, more frequent compoundings, it gives you a smaller rate per period. But you get more interest over the course of a year as you increase how often you do the compounding, and that actually levels off. If you do continuous compounding, then you get e to the RT. It's an exponential function, so it actually levels off. It doesn't go to infinity. It levels off. In fact, if you do daily compounding, it comes very close to what this is here, continuous. In fact, you'll even see some banks advertise continuous compounding, and that's what they mean. This formula here, the rate, and then time, the length of time. I have an example concerning our compound interest. So we have $1,000 at a nominal yearly rate of 5% compounded monthly. What is it worth in 5 years? So 5 years, 12 periods a year, so N is 60. The rate per period is 0.05 divided by 12. The initial principal is 1,000, and we need to raise this to 60, so you need a calculator to do that. And you get $1,283.36. Now, if you never compound it, we can compare, and that would just be $1,250. So the compounding gives you an extra $33.36. And then here I'm just showing different compoundings. Annual, once a year for 5 years. Then semi-annual, it's a little bit more. Quarterly, monthly. Then, this is pretty extreme, right? You're going from 12 to 365, and you're not even getting another dollar. And what I mentioned to you was the continuous compounding, where you do it at every instant. It's just slightly more than this, so I don't have that here listed. Checking a closed form. So every closed form in this section can be checked in two independent ways. Iterate the recurrence a few steps and compare against the formula. So basically generate the sequence by hand and then check it against the formula. Or substitute the formula back into the difference equation and confirm both steps agree. So that's kind of doing it by hand. Then there's also, there's probably other applications, but Wolfram Alpha can solve these directly. Type a recurrence at its initial conditions and it returns a closed form. So that, and now I wrote this initially before all the popular LLMs were out. I'm sure that would be yet another way that you could just give the LLM the conditions of your recurrence and ask it to come up with a formula. And I'm sure that most of the LLMs would be able to do that also. So in summary, here on the right, the first order linear equation is solved completely. That was kind of an ugly formula, and I mentioned that normally you can boil it down to a closed form that's easier to work with. A running product carries x sub 0. The sum collects the forcing terms. This again related to this general formula. Constant multiplier, no forcing terms, implies a geometric sequence, and then we derived the general formula for that. Then we applied it to compound interest, and then we just got over doing a specific example was compound interest. So coming up in lesson 3, we'll add a constant. So we had this in this lesson. Now we're going to add a constant to it. A formula for the payment on a loan and a 30-year mortgage. So we'll work through these examples. We'll talk about equilibrium points and points that reach one after finitely many steps. Non-autonomous equations where the coefficients vary with n. And then two closed forms from the young Gauss. Carl Friedrich Gauss was a very famous mathematician, and we'll show you a couple of results that he did at a very young age. So if you like this, don't forget to give it a thumbs up, and I have 4 more lessons in this series.